chambers with multiple layers. The depth has to do with more and more layers that we add through the systems that we're building. I'm not going to go in detail on how this works, but I'm going to talk a little bit about where this came from. And the first time that machine was built for newer networks was basically in the 50s. Psychologist at Cornell, Frank Rosenblatt, built hardware, and it was the Mark I perceptron. The name perceptron is also known as the algorithm for deep learning, and that's the first time this was created. This is a very complex system, some potentiometers here to adjust and some cabling. It was coupled to a camera, and was designed to read pictures, 20 by 20 pixels. And the process remains the same. What has evolved drastically is the technology behind it. Next slide. So, what is this used for? Well, for us, text processing, language translation, you can see translation happening in real time. Artificial intelligence, we have a number of applications that we use for that. Machine learning, computer vision, which is a general term for understanding what a picture or video does. This is not just the only case for the system that we built, or the use case. There's a lot more use cases in the industry. I think there's a lot of potential to adopt GPUs everywhere, and it's being done. It's kind of reaching the tipping point, the hockey stick of adoption. Next slide is going to talk about some good examples that exist today, have been for the past few years. Oil and gas being one of them. What happens there is very interesting. Basically, they put a lot of explosives on the seabed, on the seafloor, the oil and gas people, and they blow up those explosives. They have a lot of sensors. They capture all that data, the burst of data, petabytes. And then they go do an analysis, and then they do a model, visual modeling of what does the oil field look like, and what is inside. So it's very interesting. It's fraud detection, self-driving cars, diagnosis, and medical or drug discoveries, and not in a distant future, we're going to be interacting with computer that would do a full diagnosis for us without human intervention at all. Defense, intelligence, weapons simulation, security. There's a huge data center in Utah, a 3-letter agency loaded with GPUs. Data science and analytics, basically anything that has big data is fair game for GPUs to go through it. The next slide, I'm going to talk about the data center. Basically, the data center, the server, storage, and network. And this is kind of a new class of application that collaborates and works in tandem with this system to derive additional value of data. Curiosity. On the Big Sur, I don't know if you guys saw one on the floor. On the Big Sur, how many CPU cores there is? Does anybody know? And fully loaded with 8 GPUs. Cores. GPU cores. Any idea?
25,000.
Close, 30,000. 24,576. Exactly. Each GPU today, each Tesla card, M40 is equipped. It comes with 3,072 cores. So there's interesting curiosity. Speaking of bits and cores, I'm going to pass it down to Kevin, which will continue the presentation.
All right, thanks, Marcos. So my name is Kevin Lee. I'm a technical program manager at Facebook, and I'll talk to you a little bit more about Big Sur. I don't know who's been at my talk yesterday, but this one is intended to have people ask me any questions about some technologies or why we configured things that we did. So yes, again, Big Sur is Facebook's purposely built server for AI applications. So basically, the specification of Big Sur is that it supports up to 8 PCIe Gen 3 full height dual slot cards. It's designed to support standard SSI AD compliant server motherboards. It can host up to 300 watts of based on acceleration cards. It is Open Wrap V2 compatible. The server itself is a 4-only chassis, and I'll talk to why we actually went with 402. And it can do 8 2.5-inch SATA drives, so you can put SSDs or spinning hard drives in there. So the Big Sur architecture is designed around three major areas, 3 building blocks. There is a motherboard, as I mentioned, it can use standard motherboards. There is the linking board. The linking board is is the base board for the GPUs or the acceleration cards, and the hard drive and SSD back thing. So if you guys have any questions about this one, you can ask about how we did some of the interconnects and how we laid it out in the server itself. I encourage you to actually go to Facebook's or even QCT Quanta's booth to take a look at the server itself. And you can see that we use cables, PCIe cables, these SHD cables to configure different PCIe topologies depending on if you want more bandwidth from the CPU to the GPU, or you want everything on top of one CPU for the best peer-to-peer memory transfers. So Big Sur itself is modular in the way that it supports many different types of GPUs and acceleration cards. So here I show NVIDIA Tesla cards, AMD FirePro cards, the Intel 5, and a Mellanox CX4 card. So the NVIDIA Tesla card, though, Big Sur itself is designed around the NVIDIA N40 that was announced I think October of last year. So it is 7 teraflops of SGEM single point precision performance. It has 12 gigabytes of GDDR5 memory, 288 gigabytes per second of memory bandwidth from the memory to the GPU itself. Yeah, it's a pretty beastly GPU itself. So we can support 8 of them inside the Big Sur. So again, the Big Sur supports any compliant motherboard. It's 12-inch by 13-inch. You just gotta have the PCI lanes exposed so that you can connect different topologies. So actually, before I go to topology, I'll talk about Open Rack a bit. So this is actually 3 racks put beside each other, so it's kind of confusing that we put 3 racks. But in Facebook, we put 4 Big Surs in 1 rack because of power limitations in our data center. But each server, when we're running our AI applications, it's consuming about 2.5 kilowatts. So 1 rack is about 10 kilowatts of power. Yeah. So what we wanted to utilize in this flexible topology is it's called GPU Direct from NVIDIA. It gives you direct memory access, direct memory transfers, and it's one address space for all the GPUs and CPUs. And so with this, we found that having all GPUs on top of one CPU root complex, you're able to be able to do GPU Direct across all 8 GPUs at once. So typical topologies that we see in the market is like this, where there's a 2-socket CPU, 2 PLX chips, and then 4 GPUs on each PLX. So the memory transfer between GPU 0 and GPU 1 is very good because it's hosted on top of that PLX chip. However, we see that if you want to access the memory from GPU 0 to GPU 7, there's a lot of latency because you have to go through Intel's PCI. So what we did with Big Sur is that we were able to, again, change the topologies using PCI cables. So we're able to do another config, and we just call it the common config, where we put the PLX chip on top of the same CPU. So then we are able to access GPU from GPU 0 to GPU 4. They're not able to do GPU Direct peer-to-peer memory transfers. The last config is called cascaded config, and this is actually the config that we use at Facebook. And we find that there is like slight latencies actually if you even go through the CPU complex itself. So what we did, we stacked the PLX chip on top of each other, and then that enables you to do all of your GPU transfers across the PCIe switches. And with this cascaded config, actually, you can. We also looked into looking at how we can build out the cluster. So we were looking into how we're going to arrange the NICs to allow to do GPU direct across different server intra-rack. So currently, the balance config, what we did in this case, which we do see in some other OEMs, is we can place the NIC, we can move the NIC over to the PLX chips, and then the PLX from the NIC, for example, the Mellanox CX4 cards or InfiniBand cards, you can connect these NICs up to your switch, and then again, you can have direct memory access between all the GPUs inside your rack. So the common config, we were limited by the amount of PCI links we have, so we just had to stay with the same one. But again, with the cascaded config, it's the one that is the Facebook SKU. So what we can do is actually put the NIC over to the PLX chip. So the PLX chip is a PEX 8796, so we have another by 16 there. So we added a NIC there. And so it's a by 16 NIC, so you can actually put the CX4 and go up to 100 gigabits or whatever you need to put there. So if you go further up into the rack, so I just put three servers here because I didn't have space with slides. But so right here you can see that all the NICs connect up to the switch. For example, an InfiniBand switch, you can have your cluster of GPUs. So in one rack, we can have like 96 GPUs that are accessing having direct memory access across all the memory. So in this case, you can have like very large models. And video is getting really hot these days, so you can actually put your full video model onto the GPU, all the GPUs, and do your deep learning training there. So I'm going to go through a little bit about the design methodology. So there are three major areas that we were thinking of when we designed this server, and it is really serviceability. Basically, at Facebook, we care a lot about operational efficiency. So in this perspective, we want to be able to swap NICs, swap hard drives, GPUs very, very quickly when a server goes down, so that your downtime is minimized. We thought about thermal efficiency. So I don't know if you guys know, we run free air cooled data centers. So being able to be thermally efficient actually helps to the whole data center dynamics inside the thermal efficiency. And also we also put these servers mixed in between with all of our other servers, like our Type 1 servers or our Type 6 servers. So so that in itself, we needed to have it balanced within the data center. And then on the performance side, I'll show you a few numbers that we gathered, and I'll show you how we improved performance with this. So on the serviceability side, a few key areas that I wanted to point out are we made the fans hot swappable at the back. Actually, they're mounted on rails, so you can have in-rack servicing. So you can pull the rack out on these rails, and you can actually swap the fans from the front if you don't want to go into the hot app. So we also have GPUs can be removed using 2 thumb screws. So we can actually swap this GPU. I think we timed it like 30 seconds of pulling the rack out and just unscrewing the GPUs, throwing in a new one, and pushing it back in. We have removable motherboard trays. So there's 2 thumb screws. I don't think you can see it in the picture, but basically you pull that green air duct off. The 2 thumb screws, you remove all the PCIe cable. 2 thumb screws you unscrew, and the tray comes out, and the motherboard's on the tray. So you can actually service your motherboard on a card, or you can actually do it in the server itself. We also have a removable GPU baseboard, so if the PEX chip ever fails, a think those are the two only components that we're concerned about if that fails. And again, there are two thumb screws, two handles underneath the GPU itself, and you can just lift it out. On the thermal efficiency point of view, so one thing we did was we put 4 large 92mm fans. They're dual fan modules, so we can support up to 45 degrees Celsius ambient temperatures with one fan fail. So it's pretty efficient in that way. The GPUs are all placed in series, so you don't have to preheat from other GPUs. Each GPU can go up to 300 watts. The air duct is optimized so that most of the air actually goes to the GPUs itself. And it is a 4OU chassis so that we have enough room for airflow and lowering the impedance for the air. And then on the performance side, this is simply the peer-to-peer test from NVIDIA CUDA. So we can see that the bidirectional bandwidth between each GPU, all GPUs from 0 to 7 have around 24.98 to 25 gigabyte per second. And then the latency, so we see about 8 microseconds as the most, and about 6 or 7 microseconds as the least. So we optimize this thing so that it's high bandwidth and low latency, which is perfect for what we do. So that's all for our slides actually. So, but I invite you guys to ask any questions about anything in these slides.
Common memory we talked about GPUs. DRAM GPUs.
So the GPU itself has GDDR5 memory, and so when you do GPU direct, it's some CUDA functions that you can call, and then you can actually program it so that it's on one address space instead of having to care for the different GPUs itself. Yeah, actually, one thing I didn't mention about this is so we're open sourcing the hardware, but we've been continuously open sourcing a lot of the software development that we've been doing. So we mostly use Torch. It's an open source framework. Use Lua to code on top of it. But you can visit our Facebook research site, and we actually have benchmarks like GoogleNet, BGG. You can actually run. We do publish some benchmarks that you can run on these. Yes. So I think that's very application dependent. So for us, actually, we don't use too much CPU. So actually, what you saw here, 2-socket, it's like too much for what we need. But we just put it there. Any other questions?
What CPU do you use? Xeon D?
So we use the Xeon E3 2680.
Do you think Xeon D will work in this application?
We would have to rethink how we do it because so I think you talk about like the assembly platform that we have out there. So the PCI-e lanes that are exposed to the Xeon D architecture that we have currently, we just have to rethink how we're going to do the board. But I think that's a good suggestion too. If we don't care about the CPU that much, then we put the Xeon D. So microserver or something. Yeah, but we might sacrifice PCI-e lanes.
SSDs or hard drives, these walls, are they just temporary area for your GPUs to work?
Yeah, so actually we have a network attached storage that's not shown here that we connect to our data center. But yes, you're right. So we put 8 SSDs so that you can put like a staging area of like what model you want to put there, and then you would train and then you would just access it from the SSD so that you have higher bandwidth, higher speeds there. So we're still experimenting on that. We don't have numbers that we can share right now, but that is something we're looking into testing out like InfiniBand and Rocky, the remote over converged Ethernet. So we don't have those numbers yet. So at Facebook ourselves, we don't use InfiniBand, but for this architecture, we are able to use it. We're using regular Ethernet. So I think we announced Wedge 40 like last year, and we announced Wedge 100 this year. So yeah, that's enough. But so depending on what application, some applications actually care about latency a lot, but that's where you would have to trade off different switches to actually account for that. I don't think I can speak on how big the cluster is, but yeah, Jay's keynote had something there.
So serviceability, like you noticed on the logic screws versus a spring loaded latch. So is that because it's important to have a ground connection? And I know you probably don't want those to vibrate loose, but that would be the spring loaded latch versus other reasons.
So actually, during our development, we had a spring-loaded quarter-turn thumb screw so that you can actually remove the GPUs easily. We did have issues with shock and vibration, so we did put into like a more secure thumb screw into it. So yeah, great question. Yes, they're testing on active pool GPUs. We have tested in this survey, and they do work. So actually, active pool GPUs, we find that if the fan itself can cool the GPU, I think we might actually be able to gain some efficiency by having active pool GPUs instead of using the fans in the back. Other questions?
So thank you for coming. I appreciate it. If you want to see these servers, there are the Quanta booth and there's one in the Facebook booth. So just stop by and take a close look. Thank you.